Your book does a strange thing where it puts a bunch of particles in. I'm just going to look at, let's see how many particles. 4 particles in some sort of crystalline structure like that. And we're doing this, by the way, is that Boltzmann constant. It's the gas law constant per molecule. Your instructor may have mentioned it last semester. I mentioned it. People said, are we going to use it? And I said, no. And so everybody promptly forgot about it. Notice they forgot about the bond structures, and I said you should remember that. But coming back to this thing, I also said we wouldn't have to know about Boltzmann's constant. But if this is an absolute zero, no energy in the system, there's only one way I can put those molecules. They're at the different spacings determined by the crystalline lattice. If there's only one way of arranging those 4, what's the log of W? Log of 1 is 0. W is 1. There's only one way of arranging it. So log of W, if I had 40 molecules, it would be the same sort of thing. But notice the next step up, I'm going to add 1 quantum of energy. Whatever that number is. It's enough to make 1 molecule vibrate. As soon as I add 1 quantum of energy, how many ways are there to arrange that system? Slightly above absolute 0 now. Well, this one could be vibrating, this one could be vibrating, this one could be vibrating, or this could be vibrating. W is now what? 4. 2 quanta of energy. I'm raising the temperature even more. Now this one can be vibrating twice as fast. Any of them can be vibrating twice as fast. That's 4 ways of arranging the system. Or this could be vibrating, this could 5. This one and this one 6. This one and this one 7. This one and this one 8. This one and this one 9. You get the idea. There's 10 different ways of arranging those 2 quantum of energy already. And it builds up much faster as I start adding more energy to the system. So all that's happening is, as I add energy to the system, the entropy of the system is increasing. And it's an absolute number. Okay? It's not like I have to say, if I have oxygen at standard states, pressure of 1 atmosphere, in other words, whatever temperature I want to talk about it, as long as it's gaseous, until I get to the liquefaction point of oxygen, and of course, when I go below the temperature at which it liquefies, the standard state of oxygen is going to be what? Liquid. Okay. So when I'm doing entropy, it doesn't matter. It does matter what temperature I'm at, but you can see as I increase the entropy, as I increase the temperature, the entropy of the system increases, but it starts at 0 at absolute 0. That was the assumption of the third law, and that's what the statistical mechanics also tell us. So there's the third law of thermodynamics. The entropy of a pure, perfect crystal at absolute 0, 0 Kelvin, is 0. And now we can put together tables of standard molar entropies. And here's that product minus reactant rules, except instead of saying delta S0, it says absolute S0, because we can get absolute numbers. Next slide should do that. Okay, I put it down a couple of times. I don't know. Oh, that's the table I want. Let me just go back a minute. Here's the definition of entropy that we're going to use to evaluate entropy change. Okay? And it's Q reversible. Remember I talked about reversible products, the reversible properties, and we could make them equal to state properties. So if I make this definition, if I take the heat change reversible divided by the temperature at which I do it, I can calculate delta S for the system. And you say, how can you do that? And you do things like ds, dq, dt, and you do calculus, which we're not going to do. I'll come back to the slide for just a minute. But this is how we do it. We start at absolute zero. And we know the entropy is zero there. And he's taking this particular molecule, it doesn't really matter. We know the heat capacity times the temperature change gives you the heat change. And so we can calculate anywhere along this line. We just do an integration going from 0 to whatever temperature it is. The area under this gives you the entropy change. Okay? So as we go along, we can evaluate the entropy change. If we stop here, this is the entropy change going for this, not the entropy change. This is the absolute value for the entropy. Notice when we go from the solid to the liquid state, the temperature doesn't change. But what do you know about the chemical system? I'm going to go back to the other slide. Here's the solid state. Particles are all organized, they're vibrating. That's why the entropy keeps increasing, because the vibrations, as I did with that 4-particle thing, just keeps adding up and they're jiggling more and more. But eventually, when you get to the melting point, there's all sorts of random distribution. They break apart. They're no longer organized in a nice crystalline lattice. That's a big jump in the entropy change. Okay, or a big jump in the absolute entropy, which means a large number for the entropy change. Okay. Now we can do a phase change and talk about the reversible heat temperature, because if you add a little bit of heat, a little bit of this molecule or a little bit of the solid starts dissolving, you add a little bit more of it dissolves, or more of it liquefies. If you remove a little bit of heat, some of it goes back into the solid state or the organized crystalline state. Okay? So if you knew the delta H fusion divided by the freezing temperature, we get the entropy change. So that's all that's represented on that particular graph. So right here, this is we're adding heat, we're converting all the solid to eventually reaches liquid. Now as we start heating it up again, the liquid molecules are moving around more and more rapidly. And again, if we use the heat capacity, dt over T and integrate it, we can calculate the entropy anywhere along here. This gets to the boiling point, and now we have liquid going to gas. This is always a bigger entropy change than this, because it's a bigger enthalpy change than this. Okay. What did I do? Oh, I went past the slide I wanted. Backwards. So basically, the next change, if we go from liquid to gas, and here the molecules are fairly close together, they're randomly moving around pretty rapidly, but when they move into the gas phase, they're far apart, they have a much larger volume to occupy, so the entropy of the gas phase is much higher than the entropy of the liquid. In other words, you have a large entropy change from going from here to here. He also talks about going from a solute to a solution, and here the solute is packed together before it starts dissolving. Here's your liquid. This is a relatively organized state compared to the solution state, where the solute particles are distributed randomly throughout the solvent particles. So when you dissolve something, the entropy of the system increases. These are all just general statements, because some of the problems give you reactions, where you're supposed to figure out or estimate the entropy change. Here's a reaction. Do I have a positive or a negative entropy change here? And the answer is nothing. Well, you have a 50% chance of guessing right, but you wouldn't know. Here I have 7 gas molecules, here I have 6 gas molecules. This must be more random or more disorganized than this, so it's a positive entropy change, just because I have more gas molecules. If I do this, same reaction, now liquid is much more organized than gas. I only have 3 gaseous molecules as opposed to 6. So this side, the reactant side has a higher entropy than the gaseous side, than the product side, because of the fact that we have liquid molecules in there along with the gas. So the easiest way to do it is look at it and see which has more gas molecules if possible, or if you have liquid or solid, that represents a lower entropy state than if you have gases. So that's what this diagram is all about, just allowing you to estimate the entropy change in a reaction, because you'll see a question or two like that somewhere. And it's basically, the more disorganization you have, the higher the entropy. And of course we'll have numerical values too. Okay, phase transitions, there's delta H. And that could be delta H. Well, you can't see it too well. So here's delta H divided by the temperature of the transition. If this is delta H vaporization, this would be what temperature? Freezing. Did I say vaporization? I said vaporization would be T boiling, right? If this is delta H fusion, that's the conversion from the liquid to the solid, or vice versa, then this would be the freezing temperature. That's all she means by that. And that's equal to the entropy change. Let's see if I have it on this slide. For instance, when we do this change, delta H freezing or fusion is a 602 kilojoules at 273. If I want the entropy change, I would divide this number by this number. Okay. Now, one of the confusing things that starts happening here, I have to write this down, but I'll write it down right now. I talked about this, we're not going to do this, but this is certainly something we have to know now. First of all, this is temperature in kelvins. This is the heat change that's done reversibly. The units for this are going to be joules per Kelvin. Now, all the other thermodynamic properties so far that we've discussed, namely the internal energy and the enthalpy, the units are typically in kilojoules for most reactions. So when you start combining these, the big problem is to make sure you're working consistent units, either joules or kilojoules, because we're going to start combining these. But meanwhile, coming back to this, if I wanted the delta S fusion for H2O, I would take 6.02 and this is per mole over 273.15 kelvins. So if I'm talking about the delta S for a particular reaction like that, it will be this number when I divide it out, and I convert from kilojoules to joules. So it would come out in joules per K and mole, because there's 1 mole, 1 joule. Notice we're saying what? It's standard pressure, so we can say S0 for that. That's S. And there he did it for us. And he left it in kilojoules per mole per Kelvin. But typically you'd see that written as 22 joules per mole per Kelvin. And that's all you're doing is shifting the decimal point. Because that's how it's calculated if you're looking things up in tables. Here's interesting thing, Troughton's rule. By the way, when I went to school, we did it in calories, and you had to learn the number and everything. Can you see it? I like to tell a story about this, because I always talked about it in my thermochemistry or thermodynamics section when we got to it. And it's a way, if you know delta H of vaporization, you can calculate the boiling temperature because you know this constant or you memorized it. Or if you know the boiling point, you can calculate or estimate the enthalpy of vaporization. And I said, I always talked about it, and it disappeared from the textbooks, and I kept talking about it. And about 15, 20 years ago, textbooks didn't really talk about Troughton's rule anymore. Somebody took the MCAT or whatever, and they came back and said to me, you know, Troughton's rule was on the MCAT. And I said, oh, at least you got one question right. And they said, no, I couldn't remember what the constant was. So they were out of luck. But all of a sudden, I guess that story must have gotten around because a lot of the textbooks are putting Troughton's rule back into the textbooks. Now, it works best if you're doing hydrocarbons, things like propane, methane, ethane, etc., because those don't have a lot of energy of attractions between the molecules. It doesn't work as well for water because of the extensive hydrogen bonding that occurs in water. But that's Troughton's rule. I may or may not put it on the exam, but if I put it on a quiz or an exam, at the top of the page I'd probably say 87, and you'd have to know what 87 went with. Because I don't put units with my numbers. And now we want to get to the criteria for spontaneous change. And I'm going to do it the old-fashioned way, or maybe not the old-fashioned way, but one of the ways of attacking thermodynamics.